Hi everyone, it looks like we reached the most fun part about this semester, your project presentations. We will have 3 days of project presentations, today, then next Tuesday and next Thursday. With that, let me make some quick announcements before we get started. So I evaluated your survey, the survey on Canvas, where I asked you to select your preferences, whether you want to have your talk publicly available or only privately accessible. So the survey, it turned out that 28 of you would like to have the talk publicly available and 32 of you would like to have the talk only privately available, which is totally fine. So either way is fine. I just wanted to know so I can make sure that I can respect your preferences. So today we are going to have the publicly available talks, and let me just give you the brief overview of the titles or the topics of the talk so you know what you are going to expect. So we are hearing about visual recognition with a fashion dataset first. And then secondly, we have a project on pneumonia detection using CNNs. The third talk will be on using a Cycle-GAN for changing the genre of a music track. Then we will hear about earthquake forecasting using deep learning. Then after that, there will be a talk on detecting malaria using deep learning. And lastly, we'll have a talk on a neural network for fundamental analysis in stock market predictions. So with that, I think we are going to have a pretty exciting day today with all the talks. And also I wanted to note that I will set up quizzes on Canvas where you can provide feedback to each talk, and I will share the feedback anonymously with the presenters later on. So I hope the feedback will be also helpful then for the presenters. And also I will give everyone 1 point in this class for answering the quiz. So the quiz will ask you for the comment that I just mentioned, but also about a rating for the awards. So there will be 3 awards in this class. They will be computed by averaging over the 3 categories. And the 3 categories are the best oral presentation, the best visualization, and the most creative project. But that will be then mentioned in the quiz. You just have to provide your score on a scale between 1 and 10, and then I will in the end evaluate the projects and also give you the awards in the end. Okay, with that, let us get started and let's watch some presentations.
Hello everyone, we are going to talk about visual recognition with fashion dataset. Here is the outline. We'll first give you an introduction about our research background and motivation. We prepare our data through resizing the images and also data cleansing. Then we train our model and visualize it through Stat453, backpropagation, and DC-GAN. Finally, we'll give you a summary about pros and cons and our future plan for improvement. Our motivation behind this project is that now the fashion industry is a really booming business. Many people may wish to find fashion products with a certain feature while shopping. For efficiency, it could be better if we can input images and search the features instead of input text. Thus, we want to achieve something similar that can enable classifying a clothes by its image. We obtain our original data from the Kaggle, and it's pretty large, over 30 GB. We get more than 40,000 images with different ID and description that you can see from here. Then we use it to classify our images. So here's some background info. The clothing detection tools has been adapted into the fashion business quite a lot. And we search some related work. For example, the Google Image Swirl project is a search engine that is the first in the history to take both texts and images as inputs. The information was digged from the images using the novel graph analysis algorithm. And this project, we had similar motivations and adapted similar methods, but we use a pre-trained model ResNet152. We prepare our data as the following, and actually we classified our data into 6 categories that we divided through the gender and utilities. We actually find out there are some missed IDs or empty features that we cannot use to classify our images, so we delete those images for data cleaning process. And for the resizing, we can see the original size range is really large, so we resize it. For the model training progress, we use 224 times 224, which is the minimum requirement for this model training process. Then for the GAN, we use 64 times 64, which can increase our efficiency. Our objectives of this whole project is we want to use CNN to extract features and classify images. And then we'll apply the backpropagation to understand the latent features behind this model, and we can interpret this prediction better. Then we use this again to generate new clothing images. Here is our proportion that we used for training, validation, and testing.
Of our project is to classify images and extract useful features to make future prediction. To achieve this goal, we use CNN with ResNet 152 as our architecture. ResNet 152 is an improvement upon the original ResNet. It is able to expand in depth to 152 layers while exclude unnecessary complexity. We also use transfer learning technique to train the model because our dataset is relatively small, and according to research, fine-tune a small dataset on a pre-trained model with large dataset will help to increase overall performances. We train our model on the final 2 layers of the pre-trained model from PyTorch and kept the rest as default. Furthermore, we use Adam to optimize the model because it is a combined essence of the momentum method and ResProp. Here is an image of our results. Our training accuracy is above 93%, and our validation and test accuracy is above 91%. Because there isn't any obvious overfitting as the difference between train and test accuracy is less than 2%, we decided dropout is unnecessary. This slide shows the comparison between the distribution of trained dataset and predicted label. Those two distributions are very similar. This is a good thing because it shows our model do not have biases towards any class label despite some classes may have more data to train on. This slide shows how is the prediction match with the images, which looks very promising, as they all seem to match up with their assigned labels. Beyond creating a model, we want to understand how does the model works and what does it see. To achieve this objective, we employ guided backpropagation, an algorithm that allows us to see which pixel in the input has the most influence on the prediction. 12 images on the right shows its original image and its guided propagation. For predicted label 0, the backpropagation just shows an outline of the original image, while for predicted label 1, the backpack it just picks up on the handle parts. For label 2 and 3, the guided propagation picks up on faces as opposed to actual clothing. We were curious to see if there is a feature that stands out in a class and average. This slide shows the average guided propagation for label 0, 1, and 2. It is interesting the most distinct feature for label 0 is actually glasses. For label 1, it seems like it's the bottom half of a handbag. But for label 2, it picked up meaning on faces like the previous image, which opposed to label 3, even though it had faces, the average guided propagation actually picked on just a t-shirt. For label 4, it picked on sneaker, and for label 5, it picked up on a sandal. This could mean that there are more sneaker images for men and there are more sandal images for women.
So for the last part of our project, we are using the deep convolutional GAN to generate new images from what we have. We aim to train the generator and the discriminator to compete each other so that they can generate better images. So here is a quick look of what we have achieved so far using the whole dataset. The image on the left is the original ones from the dataset, and the one on the right is the generated fake ones. We can see that they bear relatively high resemblance. But in order to maximize the DC-GAN's utility, it would be better to train on a certain class, as it would be more helpful for the people who might wish to see only the products for a certain category. So we tried training with the class 1. We can see that it is relatively accurate as most of the outcomes are the women handbags, which are women accessories. The image might be kind of blurry because class 1 is a relatively small dataset. So we also tried with the class 2. We can see that as we are training with more epochs, the image quality are actually becoming better. Here is the summary of our project. The pros is that we chose ResNet 152 after a few comparisons. We tried with more pre-trained models like VGG16, DenseNet, even Inception before we made our decision. So we have a relatively high accuracy among the models. The cons are obvious as well. As we resize the images, the image becomes blurry and may lose some information that can affect our accuracies. For the future directions, first we can try to improve our backpropagation's performance, because as mentioned before, there are few times when backpropagation actually recognizes the face of the model rather than choosing the closed products as their targets. So in future, we will eliminate the unnecessary information from the image, like the body of the model. Also, the outcomes of backpropagation is grayscale, while our images are colored. So in future, we can try to find a better algorithm to capture the color dimensions in the process. And also, as the models was pre-trained with ImageNet, it may not fit our dataset well, so there are still rooms for improvement. During our experiment with the DC-GAN, we realized the importance of hyperparameters. So in future, we will try to find the optimal values to improve the DC-GAN's performance. This is the end of our presentation. Thank you for your attention.
Hello everyone. Today we have a presentation about our project. Our project is to detect pneumonia based on chest X-ray images. We use CNN in this project. Today's presentation has 3 parts. First, we will introduce our project, which is presented by me, Jason. Second, we will talk about the specific work content and what we have done so far. Xiangyu Wang will finish the second part. In the end, we will discuss the results and some problems we've got for now. Lu Yangfang will go through the third part. Now, let me introduce our project to you. Our project is inspired by these difficult times throughout the world, the severe pandemic situation caused by coronavirus. It causes a huge burden on society, including the scheduling of social resources, especially medical resources. So we are thinking about whether deep learning could be applied in medical diagnosis. Our purpose is to detect pneumonia based on chest X-ray images, and we expect that it can simplify the diagnostic process, reduce medical costs, and improve diagnostic accuracy. So I think our task is to do a classification problem on images. CNN performance will on this kind of problem. We choose it to be the basic and the main model of our project. Our data, of course, is a set of chest X-ray images. We downloaded it on Kaggle. The dataset has 5,800 images and 3 targets: normal, bacterial pneumonia, and viral pneumonia. In the experiment, we split it into training set, validation set, and test set. 60% is in the training set, 20% is in the validation set, and the rest 20% is in the test set.
Hi, I'm Xiangyu Wang. I'm about to introduce how we implement our experiment. So at first, we decided to choose VGG16 as our model because we have learned this one from the class. And after that, we decided to divide our experiment into 2 parts. For the first part, we use neural network to detect whether the patient is healthy or have pneumonia. And for the second part, we want to classify. If the patient have pneumonia, then it's infected by bacteria or virus. So after that, we start to do our experiment. For the first time, we have an accuracy about 85%, which tells us that we need to do something like hyperparameter tuning. Like what we have done in the multilayer perceptron, here it's a fully connected part. So we apply this grid search function to this part to get the best hyperparameter. And the learning rate we get is 0.001 and 0.5 dropout probability at the first hidden layer, 0.5 dropout probability at the second layer. The third layer, the same. And here we do something different at the output layer. We use sigmoid activation function. Next is the result. We get about 96.5% accuracy. I think it's relatively very good, but here is a problem, as you can see in the plot. The curve of validation set is like this. It's fluctuates dramatically, which means the model is between underfitting and overfitting. So this is a problem we need to fix later. Next, for the second part, we also do hyperparameter tuning at this fully connected part, but instead of grid search function, we use Bayes optimization because we don't have so many options to choose for parameters. So we can easily implement this part at only like about 35 iterations to get the best parameters. Here is the result. We get a learning rate about 0.001 and 0.5 dropout probability at the first hidden layer, 0.1 at the second and third hidden layer, and also the output layer we use the sigmoid activation function. Here is the result. The accuracy isn't very good, it's only 69%. And also here it's a problem. Even the mean of trained dataset and validation dataset is about the same, but the variance of validation set is a lot larger than the variance of trained dataset. But from the first iteration to the last iteration, the mean needs keep the same. So I think the network actually learned nothing during this process. So next, let my partner to introduce our conclusions.
Here is a brief conclusion of our current achievement. Firstly, we get 96% accuracy to detect whether a person has pneumonia or not. If the machine detecting can be used in medical area, it will certainly reduce the burden on medical staff and makes the medical procedure more concise. Secondly, in detecting bacteria and virus pneumonia, we haven't get a good result yet. And this is the main problem we need to solve in the future work. Now let's see the problems we get and our plans to solve it. The first problem has been mentioned before. The accuracy of part 2 is only 0.69. It is pretty low because the ratio of bacteria and virus is about 2:1, which means that even if we predict all images as bacteria, we should get about 67% accuracy. There are two reasons for this. The first one is our model is not suitable, and the other one is that there is actually no difference between images of bacteria and the virus. Currently, we suppose there is difference between them, and based on this assumption, we will try following methods to improve our model. Firstly, when we do the Bayes optimization before, we set the bound of learning rate and as
0.0001 to 0.2, bound of dropout as 0.1 to 0.5. So we plan to set a wider bound, like 0 to 0.9 for dropout. Secondly, we will also turn other parameters to find a better model, like unite in the hidden layer. Also, we may try random search to find the best combination of hyperparameters instead of Bayes optimization. We didn't use that before because it is pretty slow, but since now we can't get a good model, we plan to use it. And other models like residual net will be considered too. Another problem is the imbalance of our dataset. We have about 27% normal images and 73% pneumonia images. Under this situation, only use accuracy as metric is not suitable. So we use AUC2, which is a more robust metric. Actually, we have already used it to train the model, but the problem is there is a trade-off between accuracy and AUC. We can't find a model to get the best of them together. So our further work is to find a good balance between them. So this is all of our presentation today. Thanks for your listening.
Hi everyone, hope you're doing well and staying safe. We are Group 12 and our project is about arranging an audio track to other genres using Cycle-GAN based deep learning. Our presentation will start with me saying how we got the idea of our project and the objective of the project with related work that we got help from. Then we will introduce with method we used and show experiments and results that we have got and end the presentation with the following discussion. While all of us were interested in deep generating models, we realized that the field is heavily focused on image data, so we wanted to try something new. So we did some research and we found out that there was something called Deep Composer from Amazon Web Service. AWS Deep Composer applies the deep generated models to help users build their own creative music just with the keyword nodes they provide. To make creative music like this, in the music field there are a lot of trials to arrange specific songs to different genres to provide listeners to have new musical experience. So we decided to make a model that could change the style of music to different genres. Therefore, we set it the objective of our project to change the genre of a music track given a set of user input containing song and desired genre, and in order to do that we will use Cycle-GAN based model that is widely used in image-to-image translation and use MIDI file as an input data. The related work that we referenced is Dr. Bruno's paper, which they were also motivated from great success of using deep generated models for style transfer for images and applied generated models to transfer music style. However, they used MIDI file with complicated data preprocessing work that would generate biased results. The main method that we used is based on GAN model. As you can see from the first figure that is from Dr. Oscar's lecture, general GAN model consists of generating model and discriminating model. Generator's goal is to fool discriminator by making a good fake output which looks like real one, and discriminator's goal is to check whether the given output is fake or real. The below figures are model architecture of generator and discriminator for our model. They both are constructed with multiple convolutional layers. The main method that we were going to use is Cycle-GAN. Cycle-GAN was originally developed for image style translator. It consists of two GANs arranged in cyclic fashion and trains in unison. Model checks the quality of transfer by using both X to Y and Y to X translator. Once we transfer from X to Y, we use Y to X translator to restore original X. In the figure, dx dy denotes discriminator and gf denotes the generator.
Before we go and start code, we look up various ways to store audio information. First idea we thought was using low audio file, but we could not find any way to put those to the machine learning models. The second thing we tried was converting audio file into MIDI, which is an electrical version of a musical sheet. The right side picture illustrates how the MIDI file will present visually. However, the raw audio file have independent audios from multiple instruments, and computer could not isolate each instrument. Lastly, we look up some database that can get low MIDI files. As this is a standardized way to represent a musical instrument by a computer, we decided to use MIDI file for our dataset. The advantages of using MIDI file is that MIDI specifies the different instruments independently. There are just 128 representations of different instruments. We start from reviewing Bruner's code. The code has a problem that it uses outdated version of TensorFlow, so some functions have been removed from the TensorFlow, and it also contains some hard-coded directory connection, and it also contains unnecessary data processing which produce biased results. To fix this issue, we modified the code so that it can use the latest version of TensorFlow 1, and we also fixed the code to iterate all defined dataset at once while pre-processing. And we also let the code to utilize the command line argument while training and testing of the model. The previous work done by Bruner filtered MIDI files with time signature changes, of which first bit does not start at time 0 and the time signature is not 4x4. After filtering all these songs, it only remaining very specific tracks which does not represent the songs in the genre. Therefore, we try to remove those filters and make generalized code based on the Bruner's code. Here is the results from the generalized model. All the samples are approximately 12 seconds as we slice the song to normalize the dimension of the input while processing the data. This is the original pop song. This is the transferred version to classical. This is the original classical track. This is the transferred version to pop song. All the transferred results contain some random sounds rather than creating the appealing music. We further analyzed the reason why the model throws out such a weird result. While the data pre-processing, the model architecture only utilized one track containing information of the piano sound and dropped the others. Actually, Bruner merged all track to the piano sound, but we dropped that part because pretending all notes in MIDI file as piano sound is removing all the useful information about the instruments. However, the problem was that the machine learning code that we were working on only uses 2D tensor representing tone and time for the training. Because of the serious problem of this model, the actual input data do not represent all sounds of a song, causing model unable to learn the characteristic of its genre.
Seeing the results and the analysis for the previous experiment, we need to merge tracks to solve the mentioned issue or need to fix the code to utilize 3D tensor for input. We choose the former one. Also, to address the problem of having empty blank slices, we removed the trailing and ending white space from MIDI file before slicing. For this trial, we created 4 models with different parameters. Model 1 and 2 have 64 convolution filters per generator, but the first one has learning rate of 0.0002 and epoch of 100, while the other has learning rate of 0.0001 and epoch of 200. The third and fourth model has 128 convolution filters per generator, but we failed to train those because of I/O error while training the model on Google Colab. Lastly, the learning rate for all model linearly diminished after 50% of epoch 3. Here is the result for our second experiment. This is the original pop song track. These are the transferred results to classical. This one is from Model 1. And this one is from Model 2. This is the original classical song. These are the transferred results from pop. This one is from Model 1. And this one is for model 2. Compared with the previous result, this time it at least sounds like a song and contains a melody from the original track. But we cannot confidently say that the transfer sound belongs to either classical or pop. We need further verification on the reason why, but we came up with some possibilities. First, it is because lots of pop songs are already derived from classical songs. Second, by removing the instrument's information while merging tracks, it ruins the characteristics of each genre. Discussion and conclusion follows. We found out that there does not exist a good way to pass audio information to deep learning model. Note that using MIDI file is not a generalized approach to represent music. While the ResNet and UNet believed to be the best convolution filters for vision tasks, there is no such architectures for sound text to the best of our knowledge. Some articles use spectrogram for sound text. However, it can be only used for classification as there is no way to map spectrogram back to audio. Altogether, we conclude that the ability to use sound as an input to the machine learning architecture is limited, and thus it makes our task more challenging. Here is the reference list for our presentation, and thank you for listening.
So today we will be talking about earthquake forecasting using deep learning. My name is William Hahn, and my fellow partners are Han, Lynette, and Susan. So I will be talking about the introduction and to provide some motivation behind the project. As you guys all know, earthquakes severely impact and destroy the lives and economies of communities across the globe. A prime example of this is the 2010 Haiti earthquake, which we were all alive to see. There are currently 3 main types of prediction models: when the earthquake will occur, where it's going to occur, and how large it will be. For our project, we will be focusing on the when. To talk a little bit about some prior research, there are a few main divergences. The first is between time-independent and time-dependent models, and the second is between supervised and non-supervised artificial learning frameworks. For our project, we will be focusing on supervised learning. And I think a key note from this slide is that none of these models have actually resulted in an accurate forecast of a major earthquake to this date. Dive into the dataset. We will be using a CAGO dataset. It's a laboratory simulated continuous dataset. The X, or the input, is acoustic data, which is real-time seismic signals. And the label, or what we're trying to predict, is the time to failure, which is the time remaining until the next earthquake. And to help visualize this data, on this next slide, the top graph is the time until failure. So as you guys can see, it slowly creeps down to 0, which at this point the earthquake occurs and it resets. And the graph below that represents acoustic signal, and this basically mimics the results of a seismograph machine. And with that, I will hand it off to my fellow partners to talk more about the model and our results.
So before we actually start to train the model, I think we need to decide what input data that we want, right? So there are 2 flavors of redoing this thing. The first one is manually extract all the features. So originally we have 150,000 time slices in each training case, which this number is too big for the recurrent neural network to train, and also for each time slice, there isn't much information to learn. So we decide to split the entire training case into 1,000 chunks, and within each chunk we have 150 time slices. After that, we just extract features for each chunk separately. So here from this table, we can see for each chunk we have the minimal value, maximum value, standard deviation, average, and some quantile information. So after we finished all these steps, we have inputted data look like this, but with 1,000 rows. And the second way of doing feature extraction is just directly use a convolution neural network before the recurrent neural network. So since our data set looks like a wave data, so we can use 1D convolutional neural network to scan through it. In our case, we use 3 layers. After the first layer, because we use the strat of 10, we reduce the dimension of the input data from 150,000 to 15,000. So after this entire 3 layer, we have a input data of the sequence length will be 150 with 16 features, like aka channels for each instance. So by using this, the CNN allows the neural network to decide which feature of the wave of the input data it wants the most.
So after we selected our features, we now move on to select our models. RNN is the most common model used for time series data. However, it is very difficult to train due to the exploding and vanishing gradient problem. So the LSTM and GRU are improved architectures that are built from RNN, which are the 2 main models we are going to use for our project. The LSTM is the most common way of dealing with the vanishing gradient problem by reparameterizing the RNN. However, the major criticism towards LSTM architecture is that people question whether all components within this rather complicated structure is necessary. So 2 groups of researchers shows that the input gate and the forget gate is important, whereas the output gate is relatively unimportant. So Cho in 2014 proposed the gated recurrent unit to make each recurrent unit to adaptively capture dependencies of different timescales. And there are researchers who found that GRU outperforms the LSTM on the task of sequence modeling on data sets such as polyphonic music data and raw speech signal data. So a question that we are also interested in is that would GRU perform better than LSTM for our data set as well? And now I will pass along to Lynette, who will show us how we build our models.
Okay, now let's take a closer look at the LSTM model we built. So with the use of generator and feature extraction we mentioned in the previous slide, the LSTM model was implemented using the following parameter values. So originally, we set the epochs to 30, and then we found out that when we increase the number of training, the validation loss kept reducing. Therefore, the number of epochs were then finally set to 150, as increasing the epochs further would not result in further improvement over the validation loss, instead causing some overfitting. And the number of units in the fully collected layers of the network was set to 64, which also improved the model results with a lower validation loss. In addition, during the hyperparameter tuning, we found out that increasing the dropout value from 0.1 to 0.2 also yielded some better results. And finally, we switched the LSTM input layer with the bidirectional implementation, which further improved the result. Once we built our final model, we plotted a learning curve for the validation loss over the training and validation sets. This plot shows that the training loss reduces continually with the validation loss closely following the training loss. This trend in the loss plot confirms a good fit of our LSTM model. Following our goal, the next model we built is the GRU. So this model has 2 GRU layers. Each has 112 and 256 units. And as we discussed in the lecture, for both layers, we use tangent H for the activation function and the sigmoid for the recurrent activation functions. And other hyperparameters are similar to the LSTM setting, so that we can compare their results better. If we take a closer look at the learning curve for this model, we can confirm that this is a good fit of the GRU.
In conclusion, based on our preliminary results, LSTM and GRU gave us similar results, with LSTM doing slightly better with a loss of 2.25 versus 2.29, And our data is from Kaggle. So after our submission to Kaggle, LSTM is currently giving us a better public score of 1.58 versus 1.69. And we note here that this could be because we haven't been tuning the GRU model a lot. So in the next couple of days, we will tune more of the GRU models and we will compare the results again. If there is a difference, we are also interested in finding out the theoretical reasons behind why one model would outperform the other for our data set as well. So those will be 2 points that we will be doing in the next couple of days. Thank you.
Okay, so I think we're recording now. So if you want to go, David, go ahead.
Hi, everybody. Our project title is Detecting Malaria with Deep Learning. Malaria is a mosquito-borne disease caused by a parasite. People with malaria often experience fevers, chills, and flu-like illness. Left untreated, they may develop severe complications and die. From CDC, which stands for the Centers for Disease Control and Prevention, there were 228 million cases of malaria occurred in worldwide, and 405,000 people died in 2018. Traditional ways in detecting malaria may have two main difficulties. One is that it's really hard for laboratoriums to detect the parasite when you examine blood smears under the microscope. Another is that in some transmission-intense areas with complex conditions, fighting malaria's parasite in all ear person does not necessarily means that the illness is caused by a parasite. Our method here is to understand the algorithms and put them into applications towards the project. From the professor's comments to our proposal and the video provided, our main algorithm used would be the CNN, convolutional neural networks.
Red blood cells are visibly affected by malaria. Knowing this, we can use deep learning techniques to assess whether someone may be infected with malaria or not. Malaria is a life-threatening disease that is extremely prevalent in tropical areas where mosquitoes thrive. As can be seen by the heat map provided by treated.com, mosquitoes also thrive in lower income regions as well, which makes it more important that there are tests readily available for humans so that lives can be saved. Visual testing early can also prevent those who do not show symptoms right away to get proper treatment, since parasites can be dormant in the human body for over a year. So to carry out this, we obtained a data set from the National Library of Medicine that contains thousands of red blood cell images similar to the one shown on this slide. As can be seen from this picture, an infected red blood cell from malaria shows dark spots in the cell that a human eye can spot as malaria, but not all malaria cells are this discrete. There are some images that have subtle differences that differ from non-infected cells that a deep learning model can spot using image classification that can be missed by humans. With deep learning techniques, we can use technology to accelerate the process of detecting malaria. These cell images come from patients at the Chittagong Medical College Hospital in Bangladesh. There were 150 infected patients and 50 healthy patients used for this data. But to attain a large sample size, many cell images were taken from these patients to make the dataset split evenly on infected and non-infected malaria cells. As a baseline, we began using a model that we were comfortable with. So this first model is a multi-layer perceptron model with one hidden layer and a softmax activation function. The test accuracy from this model was not exactly quite to our liking at 67.34%. And since we were not satisfied with that accuracy, we decided to upgrade to a convolutional neural network to achieve better accuracy. And now Bobby will talk more about the results from this model.
Yeah, so we pivoted off of that multi-layer perceptron into a convolutional neural network to improve our accuracy and make an overall more accurate model. And so each of these images is a 64 by 64 image height and width, and they each had 3 color channels. And so our 2D convolution applies, our CNN model applies a 2D convolution over those input and output channels, and then it uses a strided convolution technique. And so we used 3 2D convolutions with increasing output channels, input and output channels, and we kept the stride at 2 in each of those strided convolution techniques as well. So in the first 2D convolution, we used 3 input channels and 16 output channels. And then as we increased, we went to 16 and 32, and then we went to 32 and 64 input and output channels. And so doing this, and then doing this with the stride equal to 2, reduced the dimensionality of the images and allowed for assumptions to be made about the binned subregions that strided convolution techniques do. And so, yeah, we kept that stride consistent at 2. And then in the forward method, we set our standard dropout equal to 0.25, just to prevent overfitting in the model. And we know that's not spatial dropout, that is usually preferred in the CNNs, but we felt that with standard dropout, it was giving us a good result and helping reduce the runtime on our computers. But we are aware too that because it's not spatial dropout, you know, it can cause problems in CNNs because adjacent pixels can be highly correlated. But we did decide to stick with the standard dropout in this situation. And then we use the ReLU activation function here in our 2D convolutions as well. And we set the optimizer equal to a cross entropy loss function. So the downside to using a stride of 2 and the max pool 2D call is that it runs quite slowly. And so we use 20 epochs to run through our function or our model here. And we felt that the 20 epochs gave us a perfect balance of an accurate performance with also maintaining a decently quick runtime. And so overall, we were really satisfied with these results. As you can see, it gave us an accuracy of 85% overall, but it was much better at classifying the uninfected blood cells than the infected blood cells. But then again, we're still happy with this. And so it did leave room for improvement. And as we go into our conclusion, we think that if we had enacted spatial dropout instead of standard dropout, we probably would have seen improvements in our accuracy. We used 3 2D convolutions, but we commented out a 4th that we had written out in the code just to improve runtime. And I think if we had kept that, that 4th one, we also would have seen an increase in performance. And finally, I think if we had used more epochs, we would have seen also a higher accuracy. But again, we were trying to find a perfect balance of minimizing the runtime while maximizing the performance of our model. And we felt like this was the perfect balance. And so it led us into future ideas about how malaria detection can happen and how it can be improved. And we noticed obviously that our model was much better at detecting those uninfected blood cells than infected blood cells. And we think just from theory that that healthy blood cells, by and large, may have slight differences, but will mostly look the same across most people. Whereas malaria infected blood cells can drastically differ. You saw earlier an image of a malaria infected blood cell that was quite visible under the microscope that something was wrong, but it's not like that in every situation. And so we think that those subtle differences are probably what led our model to be better at infecting the health or at classifying the healthy blood cells rather than the uninfected ones. And that's kind of the fundamental problem that we're trying to address here is we're trying to help doctors and researchers see those subtle differences that happen within those infected malaria cells. But it was really awesome to see how, you know, we were motivated to do this off of a project that's been happening at the National Institute of Health, where researchers are using convolutional neural networks to do the exact same thing and detect malaria in blood cells. And it was really cool to see how the stuff that we've learned in this class can be applied to a real world impact with practical implications. And in this case, we can see how it has the potential to save lives. And so we're really happy with what we achieved here. And we thank you for watching our video and watching our presentation. And yeah, let's see.
Hello, this is our Stat453 final project, which is called Deep Buffet, and it is a stock market prediction model based on fundamental data. I'm Elliot Kim, and my partners are Ritik Goyal and Param Gandhi. So this is the background of our project. In today's society, financial markets are critical for many different sectors. And this importance is highlighted by the fact that the total value of companies on the US stock market is equal to a whopping $34 trillion. However, despite the wealth that is possible from investing in the stock market, becoming a successful investor is very difficult because one needs to sell when a stock is overvalued and buy when a stock is undervalued. The stock prices are difficult to predict because of the volatility in the stock market as well as the many different parameters that influence stock prices. Fundamental analysis, which was championed by Warren Buffett, is a more predictable type of financial analysis than predicting purely based on stock prices. In fundamental analysis, one analyzes fundamental data such as cash flow, return on assets, capital management, and other items on a company's balance sheet and income statements to determine the fair value of a company. In essence, fundamental data is any data that affects the perceived value of a stock. Fundamental analysis is ideal for applying deep learning models due to the complex interactions between hundreds of variables. In this project, we aim to implement deep learning models to determine whether to buy, hold, or sell a stock. Thus, we aim to produce a simple output based on highly complex inputs of fundamental data. This is the motivations for our project. First, we want to determine whether to buy, hold, or sell a stock given the company's fundamental data. Second, we want to investigate whether fundamental data are good predictors for future stock prices. We also want to determine whether various deep learning models, such as MLPs, logistic regression, and others, can accurately output decisions on stock investment. Lastly, we want to create an accessible, easily used tool which can provide accurate investment decisions. These are the objectives for our project. We want to build a dataset of fundamental data obtained from various APIs that contain fundamental data of US companies and that can be easily used to train and test deep learning models. Then we want to make various models which output a decision about whether to buy, hold, or sell a stock, given the input of a company's fundamental data from quarterly financial statements. We also want to apply hyperparameter tuning, optimization, regularization, and other techniques to create the model that has the most accurate results for given test data. Lastly, we want to learn about how to apply deep learning techniques that we learned in class to a real-world dataset.
Was finding the right data sources for fundamental financial data and building the dataset. All companies are required to file quarterly financial reports with the US Securities and Exchange Commission, which is then released to the public. So we started with this dataset and built various scripts in Python to scrape, parse, clean, and organize the data directly from the SEC website, which contains numerical data from 2009 to present. So we had about 40 quarters of data for most companies, which included thousands of different features. We then picked the top 1000 features that most companies had and obtained a dataset with around 200,000 rows. But there were various problems with this dataset. Firstly, it was very sparse and had a lot of missing data. Second, there was a lot of variation in feature names across companies that should be the same. For example, some companies had revenue, whereas some companies had sales revenue, etc. etc. So we decided to scrap this dataset and find another source. We then decided to use the data from Financial Modeling Prep API, which is a company that scrapes data from SEC directly and cleans them and offers it for free as an API. So we developed various scripts which scrape various endpoints of the API to obtain a combined dataset of around 160,000 rows and 140 features or columns. This dataset was much better and had relatively few missing values. So we dropped all the rows with missing values and ended up with around 80,000 rows. The final dataset consisted of many features, some of which are as follows. Income statements, so like they're divided into different categories. The first category is income statements, which consisted of revenue, operating expenses, income, gross profit, etc., etc. Then we had balance sheets, which contains assets, debt, liabilities, inventory, cash flow statements, which consisted of investments, purchases, etc. Financial ratios and key metrics, which are calculated from the above metrics. They are enterprise value, dividend yield, earnings per share, PB ratio, price to earnings ratio, etc. And then finally, financial growth, which is just the deltas of various important features from above, like profit growth, uh, EBIT growth, EPS growth, etc., etc. In order to prepare the data for our models, we generate the target column by shifting each company's market cap up by 1 so that each training example was trying to predict the market cap for next quarter. Then we calculated deltas for each example, which is the percent difference between the current market cap and the predicted market cap. Based on this, we assigned labels to each company. For example, if the company's performance improved by more than 5%, we termed it as a buy, which is label 2. If it decreased by more than 5%, then it's a sell. Else, we just hold the stock. We then standardized all the numerical data and split it into training, validation, and test sets, which is shown as follows. We tried out various models as part of our experiments. We started with a multi-layer perceptron based on the fashion MNIST dataset from lecture with a softmax activation function and cross entropy loss. Next, we tried a logistic regression model with various hyperparameter combinations. Neither of these models performed too well, and we couldn't train past 45% accuracy. We suspected that this was because there was a class imbalance, with 45% of the labels being a label 2, and we thought that the model was just trying to predict every example to be uh, a buy, as that was the most frequent label. Upon manual inspection, we found that the market cap values were very inconsistent and error prone, so we decided to change this target parameter to stock prices. We also removed outliers from the data and increased the number of labels from 3 to 9 and balanced the frequency of the labels in the training set to around 11% each. The labels were ordered from 0 to worst, from 0, which is the worst, to 8, which is the best, based on the stock's performance in the following quarter. We then used this data on both the previous models and found much better performance in the multi-layer perceptron. Param now will talk about some of these results in detail.
Hi, my name is Param Gandhi, and I'm gonna talk about how our model performed under different circumstances. So our initial model was a multiple layer perceptron, which we trained on the first prepared data. Initially, we were getting a training accuracy of around 29%, and then we standardized the input data and tuned different parameters, like, for example, the learning rate and the hidden layers. And we brought the training accuracy up to 45%. However, this training accuracy plateaued about 40 to 45%, and we couldn't get it to improve much. So we decided to use a logistic regression model, which used a softmax activation, but that too gave us very similar results, and we couldn't improve the performance by much. And that is why we decided to look into our data set, and we found that it was predicting label 2 because our data set after cleaning and preparation wasn't balanced. So about like half of the data was under label 2, and when we inspected this, we got several errors and non-consistent data, which is why the model wasn't able to learn and generalize so well. That is why we changed our classification parameter from market capital to stock price, and we found that stock price data was more consistent. And we also increased the target labels from now 3 to 9, and balanced the training data set to contain 11% of data per label, so which added up to 9 times 11, which is almost 100%. And then we standardized the data set and began training. when we trained this on our logistic regression model with no hidden layers, it did not perform well. But then we used a multiple layer perceptron again with 3 hidden layers with 30 units each. And even though it performed about at a 20% accuracy, we only trained it for 50 epochs then, and we didn't get a chance to uh, mess around a lot with the hyperparameters. However, this 20% accuracy was with 9 labels of 11%, which had 11% of the training examples. So, in terms of frequency of data, having a 20% accuracy was actually very good, and we found that by the end of the 50th epoch, the model was still learning and still improving. And we also found that the ADAM optimizer with a very low running rate resulted in a more stable training, which is because the adapting learning rate methods that ADAM is based on performs very well on convex optimization problems. And also larger networks converge faster, and we are still trying to try out different configurations to get better performance. To conclude, the aim of this project was to automate fundamental analysis, which has long been used by reputed investors to pick attractive securities, and is a more rigorous form of investing than just pure predictions of stock prices. We have successfully shown that fundamental data can be used to make more accurate predictions about a stock's long term movement, and we aim to continue improving our model and eventually see if it can be a good tool for other people to make investments. Thank you.